We now look at conditional and biconditional statements. If P and Q are statement variables, the conditional of Q by P is if P, then Q, or P implies Q. And it is denoted as P right arrow Q. So this is red, if P then Q, or P implies Q. Now the statement P is called the hypothesis, or the antecedent, and the statement Q is called the conclusion, or the consequent. So to see the truth values, let's consider the statement. If you pass the exam, then you will pass the course. When is the instructor not being truthful? Pause the video here and consider this question. When you're ready, you may continue. Now, it would not be truthful if you pass the exam and still fail the course. But what if you fail the exam, but still pass the course? Well, the instructor would still be truthful, since the promise only says you will pass this course if the condition of passing the exam itself is satisfied. So this gives us this truth table. P implies Q is false only if the hypothesis is true and the conclusion is false. So false only if conclusion is false. Let me rewrite that, sorry. Only if hypothesis is true and the conclusion is false. Well, this is kind of unintuitive. Because we can say that if we give a false hypothesis, conditional is automatically true. So I could say, if the sky is green, then I will give everyone $1 million. And I would never lie because the sky is not green. A statement that is true by virtue of the fact that its hypothesis is false is said to be vacuously true or true by default. Let's now work with creating a truth table with conditional statements to show that P or Q implies R is logically equivalent to P implies R and Q implies R. So remember from the last lecture that the number of rows we need in the truth table is the number of statement variables, or 2 to the number of statement variables. So we have 3 statement variables here. We have P, Q, and R. So we're going to wind up needing 8 total rows. So there are our statement variable truth values. Let's now create a column for P or Q. So disjunction is false only when both statements are false. So we're going to wind up with true, 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 and then false and false. Let's now create a column for P implies R. So it's false only when the hypothesis is true and the conclusion is false. So if we look, the hypothesis is true in row 2 and the conclusion is false in row 2, so that'll be a false. And we get it again in row 4, and every other row would wind up being true. Let's create a column for Q implies R. Same rule. So row 2 would be false. And what row is that? And row 6 would be false, and every other row is true. Now let's create a column for the left-hand side. P or Q implies R. So here we're going to look at column 4 is our hypothesis. Column 3 is our conclusion. So row 2 would be false. Row 4 would be false. And row 6 would be false. Every other row is true. Finally, let's create a column for the right-hand side. So P implies R and Q implies R. So here we're looking at a conjunction between column 5 and column 6. Remember, conjunction is true only when both statements are true. So the first row would be true, the third row would be true, the fifth row would be true, and then the seventh and eighth rows are both true. Every other row would be false. So we now need to compare the truth values of these final two columns. True, true, false, false, true, true, false, false, true, true, false, false, true, 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 true. They are identical. Therefore, P or Q implies R is logically equivalent to P implies R and Q implies R, which is what we wanted to show. So proposition states that we can represent a conditional statement as a disjunction. So if P and Q are statement variables, then P implies Q is logically equivalent to not P or Q. The proof is left to the viewer. Again, you just have to create a truth table, as we did in the previous example. We can use this proposition, though, to write out the negation of a conditional statement. Let P and Q be statement variables. Then the negation of implies Q is equivalent to, by the previous proposition, the negation of not P or Q. And then using De Morgan's law and double negation, we can write this as P and not Q. So in other words, the negation of P implies Q is P and not Q. Now they're all There are alternative forms rather to the conditional. I don't want to say alternative form. Right, but we have contrapositive, the converse, and the inverse. So we let P and Q be statement variables, and we consider the conditional statement P implies Q. The contrapositive of this would be not Q implies not P. The converse is Q implies P, and the inverse is not P implies not Q. We will now prove the following proposition. Let P and Q be statement variables, then P implies Q is logically equivalent to not Q implies not P. Notice that what we're going to do here is we're going to show that a conditional statement is logically equivalent to its contrapositive. And this will be useful later in the course when we begin to study techniques of proving. So again, we're going to prove this by creating a truth table. So we have two statement variables, so we're going to need a total of 4 rows. So let's create a column for not P, and we'll also create a column for not Q. Remember, negation just switches the truth values. P implies Q is false only when the hypothesis is true and the conclusion is false, so that is row 2. Now look at not Q implies not P. So in row 2, once again, the hypothesis is true, but the conclusion is false. And it's true everywhere else. So we have true, true, false, false, true, 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 true. Those truth values are identical, so we can therefore conclude that P implies Q is logically equivalent to not Q implies not P. That is to say, we have just proven that a conditional statement is logically equivalent to its contrapositive. Now let's give the statement, if today is Easter, then tomorrow is Monday. Its contrapositive would be, if tomorrow is not Monday, then today is not Easter. Its converse would be, if tomorrow is Monday, then today is Easter. And its inverse would be, if today is not Easter, then tomorrow is not Monday. This example shows that we can easily see from this example that the contrapositive and the original conditional are saying the exact same thing. But what can we say about the converse and the inverse? Does the converse say the same thing as the original conditional? Does the inverse say the same thing as the original conditional? Well, the answer to these questions is given in the following proposition. A conditional statement is not logically equivalent to its converse, nor is it logically equivalent to its inverse. And of course, we've already proven the third statement. So in other words, if we go back, if tomorrow is Monday, then today is Easter, it's not the same thing as if today is Easter, then tomorrow is Monday. You can easily disprove that. There's 51 other weeks in which that is not true. Same thing with the inverse. If today is not Easter, then tomorrow is not Monday. Well, there's 51 weeks. That shows that is not the case. So some alternative forms to the conditional if P and Q are statement variables. P only if Q means not Q implies not P. Equivalently, of course, that is if P then Q. So P only if Q is the same thing as P implies Q. Now, if we let R and S be statement variables, R is a sufficient condition for S, means that R implies S. I've got to fix this. So this here should actually be R. So R is a necessary condition for S, means that not R implies S, or equivalently, S implies R. So a sufficient condition means that R is sufficient enough to guarantee the occurrence of S. Necessary condition means that R is necessary to guarantee the occurrence of S. In other words, if R does not occur, then it is not possible S to occur. We look again at the statement, if today is Easter, then tomorrow is Monday. We're going to rewrite this in the three ways given here, the three alternative forms. Today is Easter only if tomorrow is Monday. Today being Easter is sufficient for tomorrow to be Monday. And tomorrow being Monday is necessary for today to be Easter. And so going back to what I was saying in the previous slide, it is sufficient enough for today to be Easter to guarantee tomorrow to be Monday. However, tomorrow being Monday is necessary for today to be Easter. In other words, if tomorrow is not Monday, there is no possible way today can be Easter, since Easter always falls on a Sunday. We now look at the biconditional statement. If P and Q are statement variables, the biconditional of P and Q is P if and only if Q. This is denoted as P, a double arrow, Q. Now, often we will shorthand if and only if as IFF. So if you see an IFF, know that that means if and only if. Now, the truth table for biconditional is given. If both statements are true, then the biconditional is true. If both statements are false, the biconditional is true. In the other two cases, the biconditional is false. In other words, a biconditional is true only if both statements have the same truth value. We're now going to show that another way of writing P if and only if Q, the biconditional, is as the conjunction of two conditionals. So P if and only if Q is logically equivalent to P implies Q and Q implies P. This statement will be important, again, when we study proofs. So we're going to create a truth table. Again, we only have 2 statement variables, so we only need 4 rows. So we need a column for the biconditional. From the previous slide, we already know what that is. We need a column for if P then Q. The second row would be false and every other row would be true. And we need a column for if Q then P. The third row would be false and every other row would be true. Now what I'm going to do is I'm going to rewrite the biconditional. I actually didn't need to write it here. I'm only doing this so that I can put it next to the statement I'm comparing it to. If P then Q and if Q then P. So we're looking at the conjunction of columns 4 and 5. True only if both are true. So that's row 1 and row 4, and it's false otherwise. So we have true, true, false, 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 true, true. Therefore, we can conclude that P, if and only if Q, is logically equivalent to P implies Q and Q implies P. An alternative form to this, we can use necessary and sufficient conditions. Well, we just showed that the biconditional is logically equivalent to if P then Q and if Q then P. So we can say that R is a necessary and sufficient condition for S. It means R if and only if S. We have now studied the 5 logical connectives. So the total order of operations for all 5 logical connectives. First is negation. Second is conjunction and disjunction. When both are present, parentheses may be needed to distinguish whether conjunction occurs first or disjunction occurs first. And last is the conditional and biconditional. And again, when both are present, parentheses may be needed to distinguish which occurs first. That concludes this lesson.